So some people asked how to do that, and you can sort of look at the numbers and sort of see, like, here's my first number. The pressure was, I'm just going to make it up, 100, make up an easy number for me. And then I can look in my set of numbers for where it's about 50, like what height gave, if I started at 100, which height gets me to 50. So I can look at my sort of list of numbers and try to figure that out. I can look at my graph and try to figure that out. There's some more fine tuning you can do with Excel. And instead of doing halving, and because the pressure is coming down, I did a sort of a demo with exponential growth. So I'm just pointing out that I sort of added some demo-y things since so I did, here's the demo that we did in class. And then I have 2 other demos where I'm answering questions and people asked individually. So one of those things came up in the speed of sound. That's the first one. One of them came up in the atmospheric pressure. That's the other one. The alkali metal is an awful lot. The specific heat is an awful lot like the melting points of the alkali metals, which we did in class. And then there were 2 other things, pendulum and Ohm's law. I'm going to ask one more time if there are any questions for me up here. No. All right. So what we're going to do, so these are all just YouTube-y things. Okay. There is a polynomial fit today, and so that's just a different choice. So on lab 2 on Monday, when we were comparing for different plots to say which one we thought was best with the melting point, I skipped over polynomial because it wasn't fair, because it has more parameters, and all the other ones had 2, and that one has more, 3 or 4, and so I didn't want to put that in the mix because it wasn't a fair comparison. But sometimes it is what you want to do. So here is in 3A, a polynomial fit. And I think I'll give a demo of a polynomial fit. I sort of recorded it, but I'll also do it again here live. Linear fit behind the scenes. I'm just sending you through a series of calculations in Excel, 2 purposes. And if you get either purpose out of it, that's fine. One is just practice in like putting formulas and working in Excel. So that's one of the purposes here. And then the other thing is to just get some appreciation for what Excel is doing for you. Do you have to do it? No, Excel does it for you. But once in your life, do it. Get a little experience in Excel, see what Excel is doing for you, and then always after that, take advantage of Excel. Sea temperature is just another plot. So we can see by graphically how worried we should be about our future. And then some more data, and in that data, I'm adding in this another quantity for you to tell me about, and that's the p-value. Okay, so let's do something old. I don't know. Let's all right. Let me do the polynomial fit first, and then I'll do the p-value type of a thing. So here's I put some Excel data, so it's not marked lab, so it's not due, it's just for demo purposes. And so I'm going to download that. So I have some Excel. And some people liked, I almost never work like in the cloud. I don't like the cloud. So enable editing. So I usually always download things. So this is some data. I had I was down in the physics lab. I put a cart on an incline and let it ride down the cart. And I said, what's the position of the cart as a function of time? You don't care. You don't need to care. But let's do a graph, show you how to do a polynomial. Okay, so we know already how to make a graph. So we just go through the motions to at least start. The motions are the same. A chart is a chart. It's XY scatter. So I highlight my data and hit insert, go over to the chart region, and I like XY scatter. And I like the dots. There are a lot of dots this time. Maybe I could connect the dots this time. Something weird's going on with this data. It has one behavior here, and then it sort of has a different behavior. So one thing you have to know when you're plotting scientific data is to not always take all the data. Take the data that you want, but not all the data. So this was when it was freely falling, rolling down the incline, and then this is like it hit the bottom and like bounced. So the position was increasing, and then all of a sudden the position goes back. So something doesn't all of a sudden go up the incline unless something weird happened. And this was like it hit something at the bottom and sort of bounced. Well, I don't want that bounce. So I have to figure out how to get rid of that data. Two ways. Okay, so first I want to point at the data so I know my dividing point. If I point at a dot on Excel, it tells me the X and the Y. So here's the X is the time, it's 5.49. So that's my like dividing time between the two behaviors. That's where I'm gonna like cut off my data. Now, what do I want to do? Let's say I made a nice graph. Let's say I didn't even notice this little kink and went to layout number 9 and I labeled axes and I did all that kind of stuff. And so I have a graph and I don't want to start all over again. If that's the case, then I can just delete the data from the graph. So what was the point? 5.49. So if I have a graph, but I don't want all that data in the graph, if I delete the data, the graph will sort of update. So that's one approach. So I just deleted that data and it's gone in the graph. It's gone from Excel, it's gone from the graph. If I didn't want to throw away the data, but if I didn't want to throw the data out of Excel, but I wanted to plot without it, then I'd have to re-highlight and start plotting again. So if I don't care about the data, I could just throw it out in my chart that I've started will update. But if I want to keep the data in Excel for whatever reason, maybe I want to do something else with that data, then I'm going to have to start and just highlight and keep the data I want. But that's two different approaches of getting rid of the data. Either absolutely just positively delete it, or keep it, but sort of start the graph again and not highlight it. So in this one, here's just a different set of data. I'll do it the other way. So this is just a different set of data. And it has this crazy crap as well. So let's say I'm going to stop that one at 3.73. But let me not delete any of the data. Let me just highlight again and go up to 373 and make another chart. So either way, I can just highlight what I want and keep all the data, or I can delete the data I don't want. And it depends on the scenario, which, you know, for us, this is the data we want. So either way works. Sometimes you don't want the bad data. Sometimes you do want the bad data for something else. So, but two ways to work with that. Okay. What do I have? So here's here's my first graph of that first A and B. Okay. Now, let's say I'm down in terms of rows, I'm down in the 70s. Let's say that's not too bad, but sometimes sometimes experiments gives you thousands of lines. If I want to drag this up to the top, say there was something at the top I was interested in, I could sort of push this and it will move. And that's not too bad in this case. There wasn't too much data. Let me see if I can undo that. But another approach, and it seems counterintuitive, but you can cut the graph, scroll up to the top really quickly, and then paste the graph back in. When there's a lot of data, that trick makes a lot of sense. So let's say I made the graph, it made the graph at the bottom of my sheet, but I wanted my graph at the top of the sheet. I can drag it, but if there's a lot of data, that takes a lot of time. If there's too much data, then I'm going to cut it and paste it. Okay, but then you cut it and you say like, oh, I just lost my graph, but you didn't. It's on the clipboard. It's remembered. Okay, what's next? You know what's next? I love quick layout number 9. There's quick layout number 9. But the whole purpose of this one was to say this really is a polynomial. It's not. This one's not a cheat, but it is data that is supposed to be a polynomial, and so we have a reason for choosing polynomial, and we do. Okay. So this was just the sort of normal stuff, time in seconds. This was a position in meters. I don't like legends unless they're doing something more for me than this one is. This was, I don't know, a cart on incline. And I had 3 trials, and this one involves 1 block, so I'll call it, I don't know, the 1 block trial. Okay. And I'm not consistent with my capitalization, but anyway, so there we go. So that is a polynomial fit. And I got somehow the measuring device gave me my first time in scientific notation, and Excel picked up the scientific notation down here on this x-axis. Let me format that axis, and somewhere down here it will say, I think, numbers. And it got into scientific notation, and I don't want it in scientific notation. If if the numbers got really big or really small, I want scientific notation. But only that first number, which was close to 0, was small. Everything else was just a regular number. So let me just choose number, and that looks a little bit nicer for me. Okay, that label thing for the speed of sound graph, and some people didn't like, there's that label position. So there's how to fix that graph. There's nothing wrong with the graph, but if you didn't like it, this is the way to change it to make it the way you like it. Okay. What else do I want to tell you about polynomials before I say goodbye to this data? Let me do this weird thing, kinematic equation. Okay. Let me just do images and find the picture of the one I want. Here's the one I want. Let's just take this. Here's this formula. It's not really the one I want. Okay, well, we'll work with it. The square term gives us the acceleration, but it is what multiplies the t squared is 1/2 of a. So I'm trying to compare what Excel gave me to this. Let me get a better version. This one. Okay, so here's this equation. X equals x0 plus v0t plus 1/2 at squared. And I'm comparing that to what Excel gave me. And say use the thing says, tell me the acceleration. Well, here's what the theory says, and here's what Excel says. And they're both polynomials. That's good. The Excel has time on the x-axis. So they call it x, but we know in what we plotted that x is really t. So these x's are really t's. So the number that's by itself, 0.6388, that's the number that's by itself over here. The number that multiplies x from Excel is the number that multiplies t over here. And then the number that multiplies x squared is over here, 1/2 of a. So you got to pay attention to that 1/2. So this number that I got from Excel, 0.0517, that's not a. That's 1/2 of a. And you're just going back and forth identifying things, but the identification here is that the thing in front of the square term is 1/2 of a. So 0.0517 is 1/2 of a. So a is 2 times 0.0517. And that will screw people up. But it was like, just don't assume that what you want is the coefficient. Sometimes there's some other number in the theory. So the theory has a 1/2 in it, and you got to take care of that 1/2. All right, so that's probably a stretch rather than a question. So what did we learn? Throw out the data that you don't want. Fit to a polynomial when it's appropriate, and how to extract how to use these numbers to relate it to some theory. And it's not always just read off the number. Sometimes you have to do a little work, like multiply by 2. Okay. Now I want to show you one other thing, and then call it quits, and we'll do. So let's just find some. Let's do the heart rate data. So most people are done this. So here's the heart rate data. I'm going to make copy that data. Ooh, I need to edit, sorry. Copy that data and put it into Excel. Excel has sheets, in case you didn't know. So I'm going to add another sheet to the Excel workbook I already have, and paste that in there, and make my graph. So we know how to do that. There's my graph, quick layout number 9. Okay, all the stuff you know. And it gives us the R squared, and R squared is supposed to tell us, is this a good a fit? Does that line explain that data, yes or no? Okay, now what I want to show you is some more numbers associated with the statistics of whether this is good or not. So under File, so I'm on a lab computer, I'm not up on the web, and under File, there are some options. So File Options, and there's an add-in. So File Options, Add-ins, and I want the Analysis Toolpak, And then I'm going to say go. I don't think it works if you say okay. I think you say go. And then you say what I want, the analysis toolpak. And then you say okay. And you don't see anything. You don't see a damn thing. Okay, but if you go to data, now if you on your menu, if you go to data, you'll see data analysis over here. That's the add-in. That wasn't there normally, but it's there if I have if I do this add-in thing. Okay, so here let's do the data analysis. Let's click on data. I clicked on data. I'm clicking on data analysis. And there's all sorts of things in here. They call it regression. Excel calls it trend line because they're like business oriented. I call it fit because I'm more science oriented, and they're calling it here regression, which is more like a statistics term. Lots of people, regression is a fancy term, and I'm not high-minded like that, so I just usually call it fit. But so they're calling it regression. Okay. So here's the regression. They want the Y's. This time they want the Y's first. Give them so the Y's were the pulse. So I can come over here and I can drag from B2 to B12 in that case. Make sure I grab the same number of X's. So that's going to be A2 to A12. And so those are my Y range and my X range that I want to do this regression on, and I want to do this trend line, and I want to do this fit. I don't know what labels is. Let's check it. Residuals. So let's check that. Let's do a residual plot. Why not? Okay. So this is going to be this additional analysis beyond what we got from the trend line and the R squared. So we're going to say, okay. And one of those things was, where are you going to place it? And I didn't say anything, and its default was another sheet. So here it is on another sheet. So this is the result. So here was sheet 2. There was my plot. My R squared was 0.9763. The new sheet is 4. And there's the, where's R squared? Here's R squared. Okay, why was it not the same? I don't know why it's not the same. Good question. I will try to dig through that and figure out why this R squared is not that R squared. All right, but let me, here's the 3.74. Here's the 3.47. I must have lost a point somewhere along the way in one of them because they're giving me slightly different answers. And here's the 6337. And there's that number. Okay, so these numbers throw me off too much. Let me highlight and make the graph again. I think I didn't have one of the points in when I highlighted or something. Okay, so there was, I went from 0.57 all the way up to 15.3. And let me do this. I'm going to kill this sheet, delete the sheet, and do the analysis again. Data analysis, regression. My Y's were B2 to B12 and A2 to A12. I think that makes sense. And I'm still slightly off. I don't know what the hell I'm doing wrong, but anyway, let me carry on. So it tells you the intercept and slope and intercept. And it gives you this other thing. It gives you a lot of other things, and that you'll learn about if you take a stat course. But we're going to learn about the p-value. So our r squared was one number. And it said, was that whole equation, was the whole fit equation good? P-value breaks it up. And it's going to say, was the slope good? Was the intercept good? And r squared is supposed to be close to 1. So I'm going to make you grind through what is r squared once in your life, and then you're just going to say, thank God Excel does it. And I'm not even going to drag you through how to get a p-value, but you get one from this tool pack. And what you need to know about r squared is it's better if it's close to 1. What you should know about p-values is they're better if they're small. So these are both pretty small. They're so small, they're using scientific notation to express them. So that's good for us. That means that the data is well fit by these things, but it makes two separate. A line consists of two parts, an intercept and a slope. And so what p-value does is gives you an independent sort of verification on each. Is the slope good? Is the intercept good? So, and what statisticians will always say, statisticians never tell you that something's true. They just tell you that something's not obviously false. And so what they'll say here is that there is an intercept, that you have a heartbeat even when you're not on the elliptical machine, that you have a heartbeat, the intercept, that fits with the data. That is a good prediction. That's a reasonable prediction. That there is a slope, that your heart rate goes up when you start exercising an elliptical machine. That makes sense. That fits with the data. This won't tell you if it should be a polynomial or if it should be a power law. It will just tell you that a line is not complete correct. So if these were high values, if the p-values were like 0.3 or something like that, then you would know that a line wasn't good. So it doesn't tell you what's right. It just tells you if something's bad. But right now, since these numbers are small, it's telling you that this is a reasonable prediction. That it sort of, it makes sense to make this prediction versus not making this prediction. Just to say, you know, it doesn't tell you a straight line's better than a polynomial or a straight line's better than a power law or anything like that. But it's telling you that it's better than not. And it tells you, gives you separate information. And having an intercept makes sense, that having a slope makes sense. So all I'm ever going to ask you, I'm not going to ask you to have some big interpretation of r squared or some big interpretation of p-values. You have to know how to make the computer spit them out. And you have to know basically r squared's better if it's closer to 1. P-value is better if it's close to 0. You know, it's just a computer class. Get the computer to spit it out, and then have a quick and easy interpretation. You'll get more sophisticated interpretation in some stat class. But for us, know what should be small p-values, know what should be close to 1 r squared values. And the hard part is to file options to get that regression analysis tool pack in the first place. Okay, so that was file options, add-ins, and analysis tool pack. Go and then okay. Don't immediately hit okay. All right. Anything while I'm up here and recording? No. Okay, so I'm going to stop recording.